Hello, my name is Gabriela Suchobarova, and I'd like to present you a paper, Graph Embedding for Near Architecture Search with Input-Output Information. So in Near Architecture Search, you want to find an architecture from a search space that has the best results on an input dataset, for example, on ImageNet. And during the optimization, you need to know how good the networks are. So you need to train them and evaluate them. And that is really time consuming. So there are several speed up techniques used in NAS, and one of them are performance predictors, where you train a model to estimate the accuracy of the network based on how its architecture looks like. And one approach to that is to perform architecture embedding. So you use, for example, graph neural networks to convert the near graph into a vector. And then you can use models like random forest to perform the predictions since you have tabular data. And until now, the models that did performance prediction or the embedding models focused only on the neural graph, on the architecture. However, networks that have a different architecture may still learn something similar representation. So we try to learn what function the neural networks from the search space learn. So we created so-called I/O data, where the input is the image and outputs are some features that the network learned. Generally, that could be some feature maps in case of convolutional networks, or you can use, for example, the vector just before the final softmax layer. And to do that, we extended an existing embedding model that's arc2vec. So to illustrate how exactly we extended it, on the left, that's a graph variational autoencoder, that's arc2vec, and it takes as an input neural graphs and tries to reconstruct them. So the first output is a graph, and on the right, that's how we extended it. This is a stack of convolutions, and it processes an input image, and then it concatenates the representation of the network from arc2vec with the representation of the image. It concatenates them, and then we try to predict the output features. So here, that's a vector that's to be predicted. So that can be, for example, the vector from just before the softmax layer. And how is this model trained? So we chose a semi-supervised design of the training because we needed to pre-train some networks from NAS bench, which would take a lot of time to train a lot of them. And we needed them to extract the output features to get the I/O data. So we got a vector of size of 512. On the right, you can see how the features look like. So here you see the 600 networks, and here are the top 10 features, so the most important features on a given image. And you can see quite a large variability across the different networks. So the main result of our paper is performance prediction. So we try to predict the test set accuracy of networks from NAS bench 101, and then we report correlation with the true scores. We trained 3 models, so the original arc2vec, our I/O model, and also a baseline accuracy model. So that's really similar to the I/O model. You just don't predict the output features, you predict the accuracies of the 600 networks. And finally, we extracted embeddings from these 3 models, and we trained a random forest on them. And on the right, you can see the results, and the blue box and the green box, that's the I/O model and the accuracy model. So you can see that the semi-supervised training might bring some advantage because our results are better than the original arc2vec. Thank you for your attention. You can meet me at the conference or just contact me. The contact information is on my website.